So at this point, we're sort of at the end of the chapter. And so we have a few more topics, and then we'll have the summary and the pitfalls and assumptions that the author always likes to do at the end of the chapter. So, of course, one thing that we have not talked about is then the cache control. So he gives an example cache controller, uh, very simplistic, very high level, just to illustrate the ideas that would be used to incorporate the cache controller. Um, so in this model, we'll have a direct mapped write back, some sort of block size, some sort of cache size that gives us 1,000 blocks, 32-bit addressing. So we've got a tag, an index, and an offset, and then a valid bit and a dirty bit. And then this is a simpler cache system. So the CPU is probably just a pipeline CPU. So we'll just block the CPU until the cache is ready. So when the CPU asks for, in this case, we'll assume a RISC architecture. So if it's doing a load or store, it'll be telling it if it's a load, then we're going to read from the cache. If it's a store, we're going to write to the cache that we're making a request, what the address is, what the data is, or that we're waiting for the data. And we'll know that we're getting the data when we get the ready signal. And so then the cache also has to make those kinds of requests to the memory system, but that'll be far slower as the memory system is operating at a different clock speed. And so multiple, probably at least 100 clock cycles slower. So the way that they typically use to describe this, because we want a high performance, is we will take our Boolean logic, our Boolean functions, and reduce them down to our circuits, and those circuits will become a finite state machine, right? And so we have a set of inputs. In this case, we also maintain a state because this is a state machine. And so we can take the old state and feed it into our logic. And then our logic occurs. And from that logic, we'll update to the new state and also know what signals to send out. So we send those out as our outputs, plus our new state is then maintained, and we'll send it to a register available for us the next clock cycle. All right, this is all binary data, and as I said before, it's Boolean logic, so it's all implemented as circuits. One thing to note is there's a little bit more about state machines if you're not as familiar with the concept in Appendix A. So you can always take a look there. But there's two different types of state machines that are mentioned in the textbook, a Mealy and Mealy beginning was an M, like meal was a Y, and there's a Moore. The Mealy is the way you would think of a finite state machine in that it takes all the input, it does a bunch of crunching, and then it gives you the output, right? The Moore doesn't necessarily depend on the input state information from the prior state as much, so that some of its logic can start sending out control signals immediately, which gives it a better performance. And so that would be the kind that we would like to use for our system. But that's sort of underneath this square. And so we'll put that aside. And so here is a simple state diagram. As we've seen a state diagram before, remember we did one for the branch prediction, 2-bit branch prediction. And so here is another one. In this case, this one has 4 states. That's each of the 4 circles. And then we see, to translate from one state to another, what are we going to do? Either we're doing nothing, and then we get a request. If the request is valid and it's a hit, then we will tell the cache to provide the data if it's a load, or be ready to, in this case, if it's a write from a store, then we'll set the dirty bit. All right. So then everything's good, and we just bounce back and forth between those states. But eventually, we will exceed our block. We will get a miss. And so then we'll look at the dirty bit. If we haven't ever written to that block, because remember, we're doing a write back model here. In that case, if the block's never been modified, then we can just simply tell the block that we're going to replace that we're going to allocate on top of it from the new block. That'll take multiple clock cycles, so we can see that we circle through that state until we're all done. Alternatively, if we have the dirty bit set, because we wrote to the block with some store instructions, then we will write it out. Hopefully we have a buffer of the sufficient size for the block that we can do this very quickly and immediately proceed to marking this as ready and moving on to allocating and overriding the block contents to have the new block ready to go. And of course, we can make this much, much more elaborate. He has an online extension section in this chapter where he discusses a hardware description language and a more elaborate model if you really want to get into that. And we're not going to do that today. All right. And we could break it out into smaller steps if we want to, which would then be separate states if we wanted to further reduce how much time this takes. And we could pipeline this controller sort of like what we pipeline the CPU and have this also work across multiple cycles. We'll talk about how this is influenced by superscalar architecture a few slides later. But this is it. We're just keeping this a very small model of, to me, these 2 diagrams sort of give you this idea of what we're looking for. We're looking for a very, very, very fast, small piece of logic that can process and keep the cache moving and up to speed with the CPU. Now, in chapter 6, we'll talk more about parallel systems, but nowadays, any modern system has multiple cores. Those cores will share the same physical address space. Decades ago, I did see, it wasn't a multi-core system, it was a multi-processor system. So I did see a multi-processor system which had 2 separate processor chips, and they each had their own bus and their own motherboard and their own connection to things. It made things complicated. Fortunately, the operating system was designed for that. It was a Unix workstation, around $50,000. So quite an investment. Nowadays, we can have multiple cores in a $100 smartphone, and they will all be sharing the physical address space. So especially if you have a multi-threaded operating system or you have a program such as Photoshop where it could potentially run on multiple cores. Then what you could do is have a program that's sharing address space and it has threads that are both looking in the same address space. So that's a single address space, but for performance reasons, each core will have its own cache. So now we're separated at the level 1 cache. And so if I read a value, in this case X, and then the other CPU reads a value, in this case X, so it's the same location, and then the first CPU writes to X, we are no longer in coherence, right? And so marked in red is the fact that the second CPU's value for X is incorrect. So this is a problem. And this is a write-through cache. So as we wrote it through the cache for CPU A, we also wrote it through to the memory system. Right? So the idea is I then want, if I ask for X, I should get the most recent value, right? In a single processor system, this is pretty straightforward. I write X, I read X, I write X. The reading always gives me the write that I got. If I start adding in more processors, then processor 1 writes X, processor 2 reads X. After that's done, then I should get the new value from processor 1. If I have multiple processors write to the same location, then I should do that and see that in the same order, right? So I should see the sequence A, B, C, D. I shouldn't have A, C, B, D, right? Because I want to make sure that when I access it, that I get the same value in the same order and I get the same final value. So that's what we talk about when we're talking about coherence. So we need to enforce this in our cache system. What we could do is I don't want to have CPU B go read from memory because that's going to be slow. So when I update X, I replicate it to the other caches. Of course, that's the shared data. I also can move it around so it's not in every place, and so then it's not being monitored. And what we'll also do, and what's most commonly done, is a snooping protocol. So each cache, right, I've got my CPUs, my cache, and then a bus connecting to the main memory. So each CPU monitors that bus, much like a network where each computer might monitor the network to see if there's any traffic for it. And so I'll monitor the reads and writes and check to see if they match something that I have in my cache. If it does, I can validate and get the new value. So now we'll record the bus activity, right? Um, CPU A retrieved X from memory. CPU B retrieved X from memory. CPU A invalidates X. Therefore, CPU B removes it from the cache because it's got the wrong value, right? And then either we could replicate it, or in this case, what we'll do is we'll read it so that it ends up being a miss and we get it from memory, which has been written through, And so we have the correct value. Though to keep that memory cost down, here's the replication. The owning cache supplies the updated value. So I know that I can, since A's cache invalidated it, A's cache should be able to provide it for me. And then just think about how complex this might get when I add a level 1, a level 2, a level 3 cache. Though what typically happens is the level 3 cache isn't separated, is sort of system wide. So there's a single level 3 cache, a single main memory cache. And then what I saw for like the M series chips by Apple, each core gets its own level 1 cache, but clusters of cores share a level 2 cache, right? So the performance cores all share level 2 cache, and the efficiency cores all share level 2 cache. And we know this is going to take time to replicate across. So we'll add this enhancement to the memory hierarchy that as we write things, we'll make sure that other processors note any items that are being shared or have the same address. And we will maintain the consistency of the write order in order to make sure that the coherency is maintained. Oops. You can reorder reads, but you can't reorder writes, is sort of the consequence of this as we're building our memory hierarchy system. All right. All right. So here is the cache hierarchy. And of course, this is a 10-year-old slides. So in this particular version, this earlier ARM chip doesn't have a level 3 cache. Also, the distinction to make is the ARM chip is for a mobile device. The Intel chip is for a server device. So it's going to be a bit more robust. But the thing to me is how much they share in common, right? They both have a split instruction data cache. The L1 cache is very small. The L2 cache is about 4, 5, 6, 8 times larger. Interestingly enough, we see that it varies in size here, I guess, depending on the model. And maybe for the higher end models, we might have a larger L2 cache to make up for the fact that we don't have an L3 cache. But they both share a limited amount of set associativity, 4-way or 8-way for the data, a random replacement scheme, an approximated LRU here. Both of them have the same block size. And interestingly enough, that block size is propagated and kept the same across all 3 levels on the Intel chip and both levels on the ARM chip. And then the L2 cache, we really want to reduce the miss rate because when we miss from the L2 cache, it gets much slower, right? We can see below that. In this case, for the ARM, we're going to memory. Here, 35 clock cycles to pick up from the L3 cache. And so we've got 8-way set associativity. And then using write back. And then here, we have 16-way set associativity. So again, and much, much larger cache. So again, we're trying to reduce the miss rate as much as possible because the consequences are very slow. quite a complex system just to keep the CPU happy and fed with data and instructions. And then the other part is the translation look-aside buffer for virtual memory. So the modern ARM, a more current ARM chip has a 48-bit, 40-bit, 48-bit virtual address space. So it's much bigger than what is shown here. The physical address space is smaller. And then a variable page size starting out at the smallest 4 kilobytes, going up to several megabytes, depending on how you want to organize your pages, how much data you're trying to put inside of those pages, right? Am I trying to store a bunch of Word documents, or am I trying to store a bunch of virtual machines and their file, which can be multiple gigabytes in size? And we separate the translation look-aside buffer for the cache, instruction data, fully associative, because again, the performance is now in the main memory to the secondary storage, and therefore you want the best associativity possible. Both of them have the logic embedded in the hardware. And here, level 1 and a level 2 translation look-aside buffer. So a hierarchy even over here in the virtual memory system. So I mentioned earlier we didn't really talk about how the superscalar architecture mixes in with our memory hierarchy. Uh, since we can send out multiple requests to the memory system, what we'll do is, just like in RAM, we support having multiple banks so we can do multiple access simultaneously. We'll do the same thing in the cache. So we'll have multi-bank caches that allow multiple access, assuming, of course, there's no conflict, right? But remember, we'll have multiple programs that are being switched between it and running. We can also run multiple instructions for a single program. The Intel Core, when a block comes back, the word you actually wanted will come back first. And the cache, unlike the simple model that I mentioned earlier in the cache controller, we're not going to block. So what we'll do is, if we have a miss, you can continue sending requests, and it'll allow that those requests can be fulfilled and returned as a hit. It'll also allow multiple misses, right? And that, of course, has much more complexity. And then for initialization of data, um, such as we're loading in an array, we're loading in the first part of our program, well, in this case, data prefetching. So we're loading an array. It will look at the address of array accesses and get the block that follows on in the array so that we eventually get the entire array in a timeliest manner as possible. So we put this all together. Then we have, for our matrix multiplication example from the previous chapters, we start out with our unoptimized version running at around 1.7 to 0.8 gigaflops. We add the multimedia extensions. We unroll the loop, right? This is chapter 3, chapter 4, and then chapter 5. We block the array access so that we don't run the stride of the rows and columns, and therefore we can see that combining all these techniques, but really taking care to make sure that we understand the consequences of our memory access, we're really improving the performance. But if we look at the large program, then a factor of 3 here, a doubling performance here, and then a doubling of performance again right there. And more remarkably, even though we're doing 1,000,000 data items versus 1,000 data items, the drop off in performance is very, very small. So there are some pitfalls and all pitfalls. So we'll run through the pitfalls for looking at data. And the author admits in a textbook that he even made these mistakes. And this is a common one to do is, am I accessing words, bytes, double words? Because that affects how long items are, right? If I have 10 items and they're bytes, that's 10 bytes, right? In my little character array. If instead I have an array of doubles, then that's 10 items times 8, 80. And 80 exceeds that 64 byte block size. So I could easily exceed my block size, and therefore a byte maps to one block, whereas a word maps to a different block. Blocking, that's what the second bullet gets into, where we get the benefit of blocking. How's the data laid out in the arrays? Were they done in a row major form or a column major form? Am I accessing across blocks, or am I going to keep it myself inside of a blocked area to improve performance? All right, but large strides, that just means I'm going way over along the length of an element of an array. And of course, that's going to blow out my spatial locality and not work very well. This is a more subtle one, and it can get masked depending on the design of the hardware. If we remember from like the previous chapter, we talked about some larger scale machines. So I can have, and I mean, we see this in the M1 chip, right? We can have 8 cores, or if you do the M1 Pro, then you've got 16 cores, and then the Ultra, you've got 32 cores. Now, in this case, what they did was basically glue together smaller chips to build the bigger chips, which then means each of those chips comes with their own memory hierarchy, right? But and we also scale up the cache. All right, let's see if we can see an example of that. So we can see a mix of processors of performance cores and efficiency cores, 8 to 10, 12 to 14, 14 to 16. We can see that the bigger chips are able to address more memory, have more cores, and what they'll have where is and a unified it's not like the M1 one where they show off they do talk about the memory system. Let's see if I go back to that one because I remember that. Yeah, so here they did it for the M3. we see the instruction data cache, we see that the L2 cache, and then there is also a system cache that is shared by the entire system, including the GPU and the AI system, so that they can not have to copy around data. Plus, the AI and the GPU don't have a cache. They instead tend to basically run through the data, right, and keep moving forward as they run through their data. And so they work slightly differently. And we'll talk more about that in chapter 6. But typically, you either scale the associativity up with the number of cores uh, in the shared caches, or you end up having more conflict hits or conflicts. And so you have to evaluate those. So the metric that he used to try to evaluate performance, he then admits kind of falls down because this assumes that basically the impact of the memory system is just a solid decrease in the performance of the chip because it's blocking access, and therefore the chip is not doing anything until it fulfills its access. But in a superscalar architecture, that's no longer true. And so that's what we mean here by non-blocked access. So we'll now have a non-blocked access on our caching system, and therefore, as we make requests, we can continue to make requests. So it's much more difficult to model this, and we use simulation to do this instead. So he uses as an example here the 286. The very early PCs were definitely not intended to compete against higher end machines, not like today. And in fact, the high end Intel cores are used in supercomputers and servers and everywhere else. But back in the day, that old Intel 286, the memory system had limited access, and so they broke it into segments. And the segments were large enough that a program could run at first, but eventually the programs grew in size, the segments did not, and therefore you would have to load and unload segments, and you would have to reference different segments inside of your memory system. This was not unique to Intel. Even older mainframes had this kind of problem because, again, memory crash prices didn't start coming down until the 80s and 90s, right? And so um, that was a challenge that Intel eventually overcame, and now they have a flat memory model. One of my other machines is talking to me. Oops. All right. So that's one pitfall. Your memory system not being set up to address more memory. Implementing a virtual machine monitor not designed for virtualization. Well, that makes sense. If I did not design my 286 to do virtualization, then the other problem is I didn't design my instructions for that. And so I may have not been as careful in making sure that all of my instructions that access hardware are privileged, are protected, and only run by the operating system, especially if the operating system wasn't that robust or complete at the time, right? Something like DOS. So, two different approaches have been done over the years. Go back and fix the instruction set. And when you build a virtual machine monitor, limit how the guest OS accesses problematic instructions. Reroute them through newer instructions that block all this for older systems, or eventually rewrite the operating system itself to also better support uh, virtualization and protection, such as through virtual memory and the use of privileged instructions. So let's see. The principal locality is the big takeaway from this chapter, is something to remember. That might show up again. Definitely shows up again when we talk about it in the homework. Programs use a small part of the overall memory space and even of their own memory space. We'll talk about a different model, such as a parallel program in chapter 6, where we could have multiple instructions running all at the same time. But, most programs, especially programs that are sequential, they're only running a small sequence of instructions at any one time. And so you're inside of a small memory space. And so caching allows us to get this. We have some fast, small amounts of memory, but your entire program can still exist in larger, slower memory, which is still fast enough that we can then get to it as we're running through our program. So we'll have our L1 cache, or L2 cache, or L3 cache, our RAM system, and our disk. Right? And so then the overall memory system, as we saw here, is very influential to design of our programs and our operating system and everything else. So today, I finished up the chapter early. I don't want to jump into chapter 6. We finished about 10, 12 minutes early, and that's fine. So today we'll just end it a bit early, and I will see you on Wednesday.